This talk is going to be about ice sheets, Antarctica, Greenland, and global glaciers. And I'm looking at how they're changing today, why we should care, and how they might change in the future. Today, there are two ice sheets in the world. There's the Antarctic ice sheet, which is at the bottom of the Southern Ocean. So the Antarctic ice sheet is the biggest ice sheet in the world. And if all the ice in Antarctica melted, global sea levels could rise by 57.9 meters. There's been ice in Antarctica for 33 million years. So as long as there's a continent at the South Pole like there is today, it will be covered in ice. The Greenland ice sheet is the smaller ice sheet. The Greenland ice sheet is in the Arctic Circle, and it has a sea level equivalent of 7.36 meters sea level equivalent. So if Greenland melted, that's how much the world's sea levels would rise. And then in these two little maps, you can see the world's glaciers. And the glaciers worldwide are yellow, and they have a sea level equivalent of less than half a meter. So if all the glaciers in the world melted, they'd contribute to half a meter of sea level rise. There's other kinds of ice in the world. There's sea ice. You can see the white sea ice in the pictures here, fringed by the yellow outline. And there's ice shelves in Antarctica. And the melting of sea ice and Antarctic and ice shelves doesn't directly contribute to sea level rise, but it does have a dynamic impact on adjacent land ice. But if we go back 27,000 years to the global last glacial maximum, sea levels were 130 meters lower than today. There was a large ice sheet over America called the Laurentide ice sheet and a Cordilleran ice sheet over Western USA and Canada. There was an enlarged Greenland ice sheet, and in Europe, there was a Scandinavian ice sheet. Britain was joined to France by the English Channel land bridge due to much lower sea levels. If you look at these maps on the right of the screen here, you can see that the Laurentide ice sheet contained enough water, enough sea level equivalent to raise global sea levels by 76 meters when it melted. Antarctica was only a little bit bigger because Antarctica is constrained by the size of the continental shelf. So Antarctica sucked up an extra 10 meters of sea level rise. If we look at the ice core record of carbon dioxide over the last 800,000 years, we can see that at the last glacial maximum, global carbon dioxide was 185 parts per million. In the pre-industrial era, it was 280 parts per million. So that rise of less than 100 parts per million was enough to completely remove the Laurentide ice sheet and shrink the Greenland ice sheet, the Patagonian ice sheet, the British ice sheet, the Scandinavian ice sheet, the Cordilleran ice sheet, and to raise global sea levels by 130 meters. In 1958, when observations began at a volcano in Hawaii, global carbon dioxide was 315 parts per million. By 2019, it was 411 parts per million, and we're on track to see another record. So the question that we ask is, what is our future world? What will this huge increase in carbon dioxide do, not only to our climate, but to the world's land ice? The IPCC uses a range of scenarios to predict future climate. RCP stands for Representative Concentration Pathway, and it's a series of data sets that modelers used so that everybody's using the same data set. And the pathway that we take gives us a range of options for what we might see. So I might talk about RCP 2.6 or RCP 1.9. That means the watts per meter squared, and they equate to different levels of warming by the year 2100. RCP 1.9 is the agreement that limits climate change to less than 1.5 degrees centigrade. So that is pretty much the Paris Agreement. RCP 2.6 limits global warming to less than 2 degrees centigrade. And that's important because we often think of 2 degrees centigrade of warming as a planetary boundary or tipping point beyond which we see more significant climate change. Today, present day policies and the present day pathway we're on suggest that we're on track for RCP 4.5, and we're likely to pass this threshold of 2 degrees centigrade, and we're on track for 2.5 to 2.7 degrees centigrade. Understanding what the future world will be like is helped by comparing us to the past. And this is what some of those scenarios might give us. So we've got on the bottom here, we've got the grey line is carbon dioxide, and this is over the last 100 million years. Then this coloured line is global mean temperature, again, over the last 100 million years. And you can see that the continents change and there's significantly different orientation of these continents. By around 30 million years, the Pliocene, we have an ice sheet in Antarctica, and we have a temperature that is very much akin to where we might be with RCP 4.5. So the RCP 4.5 is likely to see us in the Pliocene world. RCP 8.5 is the highest end emission scenario, and we have to go back even further in time to have an analogous world. At the present rate, we'll exceed the carbon dioxide atmospheric concentration that we've not seen for the last 30 million years within the next couple of hundred years, by 2300 AD. So we can think of 3 different approaches to our future world. There's the sustainability world, which sees us staying below that 2 degrees centigrade of warming, or below 1.5 degrees centigrade of warming, below the planetary boundary. And that's where we are today, and we don't really want to go too much beyond that. If we follow the middle of the road scenario that we're on today, we will see a Pliocene world. And if we go to the higher end emission scenario, we might have to look to the Eocene or even the mid-Cretaceous to find something that is analogous to where we might be in the future. In Antarctica today, there are 3 ice sheets. There's the massive East Antarctic ice sheet, the smaller West Antarctic ice sheet, and then protruding towards the Arctic Circle, we have the Antarctic Peninsula. And it's surrounded by floating ice. These are the ice shelves. We've got the Ronne and the Ross ice shelf as some of the largest ice shelves in Antarctica. We've got the South Pole just there, and then we've got the Transantarctic Mountains that bifurcate Antarctica and separate West Antarctica and East Antarctica. And each of these 3 ice sheets has a really different character. The ice thickness in Antarctica is huge, and that's why it has so much sea level equivalent. This map shows ice thickness, and anything above the that's red is around 3,000 or more meters thick. And large parts of it are above 2,000 meters thick. So this is a huge volume of ice. If you went and stood in the middle of East Antarctica, if you went to the South Pole and looked around you, all you would be able to see in every direction is just a flat, white, arid, dry, windy surface. And all the topography is buried by thousands of meters of ice. But if we took the ice away, Antarctica looks very different. It is a land of mountains and valleys. You can see the spine of mountains from the Antarctic Peninsula that projects north towards the Antarctic Circle. And you can see the Transantarctic Mountains that bifurcate the West and East Antarctic ice sheets. The East Antarctic ice sheet is largely grounded above sea level. So if you took away the ice sheet, you would have a series of land and islands. You would have a continent there. So in East Antarctica, most of the land there is above sea level. But you can see there's also a large amount of light blue to the east of these Transantarctic Mountains. And this light blue is areas below sea level. So parts of East Antarctica have a bed that is below sea level. And then we have West Antarctica. West Antarctica is not the biggest ice sheet in the world. It has a sea level equivalent of less than 5.5 meters, much, much smaller than the East Antarctic ice sheet. But you can see that much of West Antarctica is grounded below sea level. And in fact, you can see that the blues darken and deepen towards the center of the ice sheet. So in West Antarctica, the bed has a reverse slope. So the bed gets deeper towards the center of the ice sheet. Two glaciers that are very significant are Pine Island Glacier and Thwaites Glacier. Both of these huge ice streams are grounded on a reverse bed slope. So the ice gets thicker as the bed deepens towards the center of the ice sheet. And Antarctica is surrounded by floating ice shelves. These ice shelves have their own mass balance. They receive snowfall from the atmosphere, and marine water may freeze onto them at the base. Most of Antarctica's mass loss occurs through these ice shelves. So there's very little surface melt in Antarctica. Most of the mass lost is through carving of icebergs or melting at the grounding line or underneath these ice shelves. These ice shelves also play a really important role in holding back the glaciers on land. When we remove the ice shelves, the glaciers on land accelerate and discharge more ice into the ocean. Around West Antarctica, areas are thinning and losing mass. So in this map here, you've got areas in red that are losing mass. And you can see the two areas that are losing the most mass are again Pine Island Glacier and Thwaites Glacier. There are significant places losing mass along the Antarctic Peninsula, and some parts of East Antarctica, like Totten Glacier, are losing mass as well. But large parts of East Antarctica are relatively stable, with only minor glacier recession or negligible glacier recession. And you can see that some of these ice shelves are actually thickening around the East Antarctic ice sheet. But in West Antarctica, Pine Island Glacier and Thwaites Glacier are thinning. The grounding line, which is the point at which the ice starts to float, which you can see in this map as the black, solid black line, is receding back into the ice sheet. It's very cold in Antarctica, and surface melt at Pine Island Glacier and Thwaites Glacier is fairly minimal. What instead is happening is that changes in oceanic circulation are melting this ice sheet from below. This is a giant that's been awoken by warm ocean currents that can now penetrate underneath these floating ice shelves and melt the glaciers from below. So you can see here the grounding zone with a big blue circle here. And here we are observing very rapid changes. These glaciers are unstable. They cannot stabilize on this reverse bed slope, and it's likely that they will now start to recede very rapidly due to this challenging configuration. Today, Pine Island Glacier and Thwaites Glacier are driving sea level contribution from Antarctica. In Antarctica from 2012 to 2017, there was at least 0.5 millimeter and up to 2/3 of a millimeter sea level rise per year. This graph is a graph of change in thickness over time. So DH is change in thickness and DT is over time. And you can see the really strong thinning rates where it says ASC, which is the Amundsen Sea embayment by Pine Island Glacier and Thwaites Glacier. So Antarctica is contributing around 1/3 of global sea level rise from land ice. If we look at the Antarctic ice sheet into the future, we can estimate how much sea level contribution there will be under different climate scenarios. So a global warming of 2 degrees centigrade above pre-industrial West Antarctica is unable to sustain itself and will inevitably collapse. So we have 1 degree centigrade of warming. We're likely to see about 1.5 meters sea level equivalent from Antarctica. For 2 degrees warming, we're likely to see about 2.5 meters. And for 4 degrees centigrade of warming, we could see over 6 meters sea level rise just from Antarctica. And you can see that this is related to the disintegration of the West Antarctic ice sheet. The West Antarctic ice sheet's recession will be unstoppable once a certain threshold is released. It's difficult these numbers here are not likely to happen in our lifetimes or in the next few hundred years. This is models that are run to equilibrium. But this is the kind of scenario that we could live in if we continue to warm the world and we don't make any changes. And we can look to the past. This is the Pliocene Antarctic ice sheet. This is a numerical model of what the Antarctic ice sheet looked like around 4.23 million years ago in the warmest part of the Pliocene. Atmospheric carbon dioxide was about 365 to 415 parts per million, and the Antarctic ice sheet occupied a slightly different place, but it was still at the South Pole. After 5,000 years of those conditions, there was 10.4 meters of sea level rise from Antarctica, largely produced by the West Antarctic ice sheet. So the question is how much and how fast? This simulation predicts sea level contribution from Antarctica by the year 2100. And in grey, we have sea level contribution from Greenland, and we have sea level contribution from Antarctica. And this simulation is quite clever because it integrates an ocean model as well as the 2 ice sheet models. So it can look at the impact of changing ocean circulation as a response to the freshwater forcing from the melting land ice and how that affects each ice sheet. This model suggests that if we follow this middle of the road scenario, RCP 4.5, by the year 2100, we can see around 46 millimeters of sea level rise from Antarctica and 140 millimeters of sea level rise under a higher emissions scenario. If we project this forwards to the year 2500, you can see that the sea level contributions for the different representative concentration pathways is really very variable. This is 2 simulations. One uses a process called marine ice cliff instability and one does not use marine ice cliff instability. And in this paper, Tamsin Edwards argued that marine ice cliff instability overestimated Antarctic ice sheet contributions. But you can still see that under RCP 4.5, by the year 2300, we would see several meters of sea level rise from Antarctica. And by the year 2500, we could have over 5 meters sea level rise under RCP 4.5. Whereas if we stick with RCP 2.6 and we have a much more moderate influence on our climate by not continuing to force carbon emissions, we would have significantly lower contributions to sea level rise by the year 2300, with probably less than a meter. So these are our options. Let's move to Greenland. This is the Greenland ice sheet. Again, we have a huge ice thickness, around 3,000 meters thick in its center. And you can see from this map of bed topography that again, the center is grounded well below sea level. However, the process of marine ice sheet instability is less pronounced in Greenland. We don't quite have the same situation of a reverse bed slope. And the final graph here is velocity. And you can see in red places where we have extremely fast ice velocities. And these are the ice streams, the dynamic corridors of fast flowing ice that drain the Greenland ice sheet. And Greenland is also melting. It's contributed around 10 millimeters of sea level rise over the last 20 years. And it currently contributes 244 billion tons of ice every year. That change in ice is that sea level rise is driven partly by increased surface melt. It's so warm in Greenland that sometimes it melts across the entire surface of the ice sheet in some summers. Surface melt in Greenland has been increasing rapidly, and we're seeing significantly more meltwater being produced, both on the surface of the ice and reaching the bed of the ice. But ocean forcing is also important here, and warm ocean currents are driving a very substantial increase in ice discharge. So the ocean itself is warming the marine terminating ice streams, and it's causing more calving of icebergs, more basal melt, and recession of the grounding lines. And today, around half the melt of Greenland is due to surface melt, and around half of the mass loss is due to this dynamic change as a result of ocean forcing. You can see that the contribution to sea level rise from Greenland has now overtaken Antarctica. So Greenland now contributes more to sea level rise. Greenland is in blue here, and Antarctica is on the red. And as we move more towards the present time, Greenland has overtaken Antarctica and now contributes more to sea level rise. Warmer summers and warmer winters are increasing the melt area of Greenland, and it's changing the albedo. There are a number of positive feedback effects in Greenland. Things like increased dust on the ice surface, smaller areas of snowfall remaining through the summer are darkening the ice surface in Greenland. And darker surfaces absorb more energy, and that increases the melt of the glaciers. And the changes in ocean circulation and increases in ocean temperature are driving the recession of these glaciers. Under the best case scenario, Greenland will be contributing a minimum of 1 millimeter per year to global sea level rise, and that's under 1.5 degrees centigrade of warming. If we think about where it might be in the future, we can suggest that by the year 2040, we may have a total of around 35 millimeters. Today, the ice discharge in Greenland is tracking along the highest scenarios. We need to work extremely hard to bring down the ice discharge from Greenland by reducing global warming so that we reduce the amount of sea level rise. If we continue on this pathway, by the year 2100, we could have 25 centimeters of sea level rise from Greenland alone. And we can go back to this map as well. So this is from the same study I showed you earlier. We have the partition of sea level contribution from Greenland and from Antarctica. And this study suggests that under RCP 4.5, which is the lower scenario, the middle of the road scenario, we could have 109 millimeters of sea level rise by the year 2100, and significantly higher under a higher scenario, RCP 8.5, which is the lower graph here. It's not just Greenland and Antarctica. Worldwide, glaciers are shrinking. These are Landsat images from Columbia Glacier in Alaska from 1986 to 2019. And you can see the really dramatic recession of this glacier and all the other glaciers in this area as well. Worldwide, these glaciers are losing more mass than is being replenished each winter by increased snowfall. Patagonia and Alaska are some of the world's largest contributors to sea level rise. From 1961 to 2016, globally, glaciers have contributed 9,625 billion tons of ice to the ocean. Alaska has contributed 3,000 billion tons of ice to global sea level rise between 1961 and 2016. And that is approximately equivalent to just under 3 millimeters of sea level rise. These glaciers are not just important for global sea level rise. Globally, glaciers are an absolutely critical freshwater resource. And as they recede, that resource is threatened. Globally, glaciers are also important because as they shrink, there is an increased risk of glacier hazards, with things like glacier lake outburst floods becoming more risky as globally glacier lakes are growing. We can think of the world's mountains as water towers. This is a project that I was involved in that was published earlier this year. Globally, mountains produce water. All the air that streams over mountains is forced to rise, where it condenses into precipitation, and that precipitation is stored in glaciers and snow and ice. So globally, glaciers are not only producing, but they're also storing water. That water is then released slowly to people who live downstream. So people can access that water for irrigation, for industry, for hydropower, and for domestic consumption. These mountain water towers provide a critical buffer to drought because the meltwater from glaciers can comprise a large proportion of the downstream runoff. Globally, a third of the world's population lives downstream of these mountain water towers and would be directly impacted by the loss of glaciers. And 250 million people worldwide live directly within these water tower catchments. In this project, we categorized the supply and the demand for every water tower in the world. We defined a water tower as being a mountain intersected with a drainage basin, and it had to have snow and ice and glaciers on it. So mountains in places without glaciers, we didn't include them in our water tower assessment. So in blue here, we have the production of water for Asia, North America, South America, and Europe. And you can see that there is a variation in the amount of water that these glaciers are producing and storing from precipitation, snow, glaciers, and lakes. So in Europe, the Arctic Ocean islands, Scandinavia, Iceland, and Sweden, for example, are all producing a lot of water. And in South America, South Chile, La Puna, and South Argentina are important for producing a lot of water. In Asia, the Tarim interior, the Indus Basin, and the Tibetan Plateau are also very important for producing water. In brown, you can see the demand for these water towers. So we have demand from industry, demand from irrigation, demand from domestic consumption, and demand from natural systems. In Asia and Oceania, there is a huge demand for water. From Amu Darya, the Tarim interior, and Indus are all using this water for these purposes. In Europe, you can see that the Urals, Volga, the Danube, all of these areas have a large demand of water. We derived a water towers index by looking to see how much water was supplied by these mountain water towers versus how much water was demanded. So a water tower is very important if it's both producing lots of water and there's also lots of demand for lots of water. So you'll see that Iceland, for example, produces a lot of water in Europe, but there's very little demand for that water. It's all just draining into the ocean. So Iceland ranks very low on our water towers index. Whereas in Asia, the Tarim, Amu, Indus, these places are producing lots of water and there's a huge demand for that water. So they are ranked very highly by our water towers index. Globally, we can think about the importance of these mountain water towers within the framework of glacier recession by considering peak water. Because glaciers melt, as they melt, they produce this meltwater. If you increase air temperatures, the glaciers will melt more. As the glaciers are melting more, they will produce more meltwater. So it's a fantastic time. You can plant avocados, you can irrigate your crops, you can build some hydropower stations. Ultimately, as the glacier volume continues to decline with rising air temperatures, which you can see happening in this green line, the meltwater will slow down and shrink. And eventually, you'll pass peak water and your runoff each year will be smaller and smaller. This will result in water shortages in these dependent high mountain areas. This glacier recession means that the annual runoff will eventually become smaller than it has been in the past, and the glaciers will be unable to produce enough meltwater to meet demand. We can calculate when peak meltwater will be using various different modeling techniques. And you can see that in parts of the world that are colored in red, we've already passed peak water. So we have peak water already passed in the 1980s in places like Peru and Bolivia. The Baker River has already passed peak water in South America. In North America, the Fraser, Mackenzie, and Columbia areas have already all passed peak water, and meltwater will decline from then on. The Rhone in Europe is likely to have already passed peak water, and you can see the meltwater runoff declining from now on. 1/3 of the world's population lives in these catchments, and if they have already passed peak water, then they will be receiving decreased water resources. The places most vulnerable are the Northern Andes, the Himalaya, the Swiss Alps, and Alaska. Because these global glaciers are shrinking, it is inevitable that peak water will pass and result in increasing water risk in these downstream areas. So you can see significant contributions to sea level rise from places like Alaska and South America. High Mountain Asia has a smaller circle. This is ASC here, High Mountain Asia. There's a smaller circle because the volume of ice here is very small, but the population that live downstream of these mountain areas is very dependent on the meltwater produced. We can project glaciers and ice caps forward in time to predict future sea level rise. Under RCP 2.6, we can have a relatively small amount of sea level rise from glaciers and ice caps of perhaps around 79 millimeters under RCP 2.6. But under RCP 8.5, we can have up to 159 millimeters of sea level rise from glaciers and ice caps alone. I want to look in a little bit more detail to the Himalaya, because this is where the global water towers are most critical. In blue here, we have the glaciers. And then we have overlain on that, we have some bar charts. If it's red, that means that there is a thickness reduction and the glaciers are thinning. And then we have in blue places where glaciers are thickening or growing and have a positive mass balance. So you can see that overwhelmingly, we have a glacier negative mass balance with these glaciers thinning almost uniformly across the Himalaya. The Himalaya is using a large amount of hydropower. So we have hydropower here in dark blue circles, that is installed capacity, and the potential capacity is the light blue circles. So there is a huge amount of hydropower being installed in China, India, Nepal, Pakistan, Bangladesh. All of these places are powering their economies with hydropower. And then all across the Indian subcontinent, you can see vast scale of irrigation. So in this second graph, in blue there, we have zone of irrigation development. And you can see that there is extensive irrigation in these areas. This is a hugely populous region with vast demands on the water. And the Indus in our ranking system comes out globally as the most critical water tower. And so we give it a ranking of 1. And everything else is measured in our water towers index as relative to that. But you can see that Amu Darya, the Tarim Interior, the Indus are all hugely important water towers. They have an important water supply role, producing precipitation, glaciers, snow, and surface water And downstream, these basins are hugely populated and heavily irrigated, so they also score very highly on our demand irrigator. There is already a water gap in this area. There is a gap between the water demanded from here and the water supplied, and that gap is currently being filled by unsustainable use of groundwater. If you look at where we'll be by the year 2050, here we have graphs for our range of IPCC scenarios. And you can see that for the Indus Basin, we will lose significant amounts of our area if we continue on the higher end emission scenarios. Whereas if we stick to 1.5 degrees centigrade of warming, which is the blue line in this bigger graph over here, then we will keep around 20%, we'll keep around 80% of these glaciers and only lose around 20%. We ranked each water tower on the basis of its vulnerabilities. So we have these little spider plots, and they go from top to bottom. They go through hydropolitical tension, changes in GDP, changes in population, changes in precipitation and temperature, government effectiveness, and baseline water stress. And then these are our 5 water towers that we can look at in more detail, coloured according to their water tower ranking. And the Indus is highly vulnerable because the demands on the water are likely to increase due to increased GDP and increased population. This area is also projected to warm, and that warming is likely to drive recession of these glaciers. It is also important that there is a transboundary basin within this drainage basin. The nations do not line up nicely with the watersheds, and there is hydropolitical tension between all of these countries like Pakistan, India, China, and Afghanistan, with limited government effectiveness. If we have increasing demand but shrinking glaciers, there will be increased water tension, and government effectiveness is critical to avoid geopolitical tensions and fighting over water. That is where we will be if we follow the higher end emissions scenarios. So I've thrown a lot of numbers around today, and they come from a variety of sources. But I wanted to just kind of hone it down that globally, land ice is contributing around 665 billion tons of ice every year to the ocean. And that's resulting in nearly 2 millimeters of sea level rise from melting land ice alone. So globally, contributions from Greenland, from Antarctica, and from global glaciers are driving sea level rise. Recently, Greenland has overtaken glaciers and Antarctica as the biggest contributor to global sea level rise. But overall, the biggest threat to our coastlines comes from West Antarctica, because it has this instability due to a reverse bed slope, which has the potential to drive rapid and irreversible ice loss. It's therefore critical to limit global warming to 1.5 degrees centigrade. The majority of the land ice will remain under the lower end scenario of RCP 2.6. Here we've got graphs E, F, and G. E is Greenland ice sheet mass loss, F is Antarctic ice mass loss, and G is glaciers and ice caps. And there we have the blue line is RCP 2.6, and the red lines are RCP 8.5. And along the small graphs, we go to 2100, and in the big graph, we go to 2300. If we follow RCP 2.6, then we can expect around 0.43 meters or 43 centimeters of sea level rise from all of these land ice sources by 2100. But at the higher end scenario, we could have nearly 1 meter by 2100. So under the higher end scenarios, we not only have flooding of our coastal areas due to ice sheet loss, we also have water shortages for 1/3 of the world's population due to the loss of glaciers and ice caps. Our pathways to limit global warming to 1.5 degrees centigrade are getting increasingly challenging the longer we leave it. It's increasingly challenging to do this without large-scale negative emissions, which is sequestering carbon dioxide. You can see here the pathway that we need to follow in green for the 1.5 degrees centigrade of warming. This has a small overshoot and then comes down. Our current warming rate suggests that we would pass 1.5 degrees centigrade in the next 20 years. If we want to follow this pathway and stop the warming and continue to maintain a less than 1.5 degrees centigrade of warming, we really need to have a really rapid reduction in carbon dioxide emissions globally. Some take-home messages. Globally, glaciers cover only about 0.5% of the global landmass, and they only have about 40 centimeters of sea level equivalent. And globally, they are receding, contributing less than 1 millimeter of sea level rise per year. This may seem insignificant until you realize that whole populations, whole cities are reliant on these glaciers for their water supply. Glaciers provide critical water resources to 1.9 billion people. And these water resources are threatened as these mountain water towers reach peak water, with contribution from glaciers to downstream communities declining worldwide. This is likely to increase water stress because under increasing populations and increasing GDPs, demands are likely to increase, but the supply is projected to decrease, especially in the dry season. If we want to avoid the worst impacts of climate change, we must stay under 1.5 degrees centigrade of warming to ensure water security and ensure our coasts remain not inundated for millions of people. And that means that we must aim to reduce carbon dioxide to net zero by the year 2050. Okay, I will stop sharing. And I can take any questions. Oh, there's been a lot of activity in the chat here. Is there a difference between sea ice and icebergs? That's a great question. And yes, there is a difference between sea ice and icebergs, even though icebergs might float in sea ice. Icebergs are the frozen parts of glaciers that have carved off the glacier and floated away. So you can think of an iceberg as land ice. Icebergs were from snowfall that precipitated on land, and they have carved off the end like you see in chasing ice, and then they floated away. If you increase the number of icebergs or the volume of icebergs in the sea, then you're increasing discharge to the ocean, and that will contribute to sea level rise. Sea ice is frozen seawater. So sea ice is ephemeral, it comes and goes. In the Arctic Ocean, we get some multi-layer sea ice, multi-year sea ice, because of the nature of the Arctic Ocean, which is all constrained by land all around it. And in Antarctica, the sea ice spreads out over quite a big area. But every year we have a sea ice minimum and maximum as the sea ice grows. Is Greenland melting faster than Antarctica? Yes, Greenland is now melting slightly faster than Antarctica, but it's likely that eventually Antarctica will be the leading cause of global sea level rise. But in the last few years, just the last 5 years maybe, Greenland has overtaken as the biggest contributor to global sea level rise worldwide. What is the major contributor to surface dust in the Greenland area? Pollution, wildfires, various things like this. Can icebergs cool the ocean? It's a really interesting question. If we increase ice discharge into the ocean by increasing basal melt from underneath these marine terminating ice streams, or by carving more icebergs out into the ocean, then you would see a cooling effect. And in fact, during the last glaciation, we saw regular large armadas of icebergs being released from the Laurentide ice sheet. It seems that the Laurentide ice sheet had a dynamic instability and would periodically undergo a massive recession and release large amounts of icebergs into the North Atlantic. And in Britain, we see the impact, because in Britain, at the same time that these icebergs are released into the Atlantic Ocean, we get glaciers advancing in Britain. If you put enough icebergs into the ocean, you can certainly cool it. Would water resource security benefit from more projects like ice stupers? So citizen science to find ways to manage water supply is something that is a really hot topic at the moment. Lots of people are working on this. And there's a lot of interest in getting traditional methods to conserve and use water more effectively and to use these in the mountains. So in places like Peru, some people are trying to work with local communities to bring back traditional methods of archiving and using and storing water to manage it more effectively. Will glaciers and melting ice caps make the sea less saline? Probably not from glaciers and ice caps. There's probably not enough volume of ice to do that. Even if we melt the large ice sheets, I don't think there'll be enough water to do that. There's just, the ocean's just really, really big. Really, really, really big. Excellent. There's a question here, what is the albedo effect? I think the albedo effect is where something is darker. So one of the reasons why we have polar amplification of climate change is that sea ice, this frozen seawater, is really white. It's bright white, and snow is bright white. Whereas the ocean is dark, and ice, glacier ice, is grey and it's dark. And if it's darker, then it absorbs more energy and it's warming. So if something is very white, it reflects a lot of energy back into the sun. And if you get a shipping container and you paint it black and you paint another one white, and it's a hot summer's day, you'll notice very quickly that it becomes a lot warmer in the black one than it does inside the bright white one. And it's why we give runners, when they finish marathons, highly reflective, these space blankets to keep them warm after they finish their marathon. So if you change the albedo, then you change the surface energy balance of the ice, and you'll increase the melt. How do I know what Antarctica looked like in the Pliocene? That is such a great question. There are a number of ways in which we know what Antarctica looked like in the Pliocene. One of the ways we know is by looking at marine sediment cores. So we have a huge international drilling program. And Antarctica is, for geopolitical reasons, Antarctica is a really interesting place to work because you have international cooperation and it's not owned by anyone. So we have these huge international ocean drilling programs like the IODP, the International Ocean Drilling Program. And they've taken very, very long sediment cores off the continental shelf edge. And you get sediments that tell us about the Antarctic ice sheet through time, and they can go back millions of years. And that's how we know when the Antarctic ice sheet was present. And we can look at the minerals, and we can look at the sediments, and we can look at the various proxies within these cores, the various animals, the fossils in the cores, and the distribution of clay minerals and things like that. And they tell us about how big the Antarctic ice sheet was. So for example, Pine Island Glacier goes over some distinctive bedrock. If you have a sediment core and you have some of that distinctive bedrock being transferred to your sediment core that's miles away off the continental shelf edge, then that says that that bedrock has been eroded by the ice and icebergs are carrying bits of that bedrock over your core site and dropping it out. If you suddenly get none of that bedrock, then that suggests that the ice is no longer eroding that portion of the bedrock. So there are a number of different ways in which we can do that. There are also some really clever things. So for example, Antarctica is volcanically active, and there are a number of Pliocene volcanoes on Antarctica. And these Pliocene volcanoes erupted under the ice and made a weird and wonderful volcanic rock formations. And they form a characteristic formation that tells you about the ice surface elevation. And we can date them using things like argon-argon dating and zircon dating. So we can see how old these rock formations are, and we can then make inferences about the height of the ice. Ice cores only really go back around 800,000 years. The ice core carbon dioxide record I showed is about the longest we have available. How would sea level rise affect tectonic activity? I think you'd have to ask a sea level rise specialist rather than a land ice glaciologist that question. That is a really interesting question, but I don't know the answer to that question off the top of my head. I do know that if you reduce land ice, that does increase tectonic activity because of the unloading effect on the mantle. So if you reduce the amount of the weight of the land ice, we're likely to get more earthquakes in those places. So if you change the distribution of mass on the planet, this will induce earthquakes. Internship programs recommended for teens. You mean for policy or for fieldwork, or I'm not quite sure what you're looking at there. Okay, for fieldwork. Okay, well, there's all sorts of things. There's the British Schools Exploring Society. There's various teenage expedition groups that you can go in. I went on a British Schools Exploring Society expedition at the age of 17, and that was fairly transformative for me. There's also the Nuffield Bursary. The Nuffield Bursary is for A-level students, and at Royal Holloway we host Nuffield Bursary students who can come in and work in our labs and work with us on our research projects and get experience in that way. The Royal Geographical Society has an awful lot of resources that explain how you can get involved in those kinds of things. So if you have teenagers who are interested in getting out into the field, I recommend getting involved with the Royal Geographical Society. Oh, building underwater walls. I had read a proposed solution to protecting vulnerable glaciers was to build underwater walls on the seafloor to stop ice sheets sliding and resulting in sea level rise. Do you think this is feasible? No, this is not feasible. I've heard other people talk about this before, but the scale of these huge glaciers is absolutely enormous. The underwater engineering that you would have to do to try and prevent marine currents from getting around them and into the ocean and underneath the ice sheet is completely unfeasible. I mean, if you go to the north coast of Britain, we can't even stop the sea level there eroding half of eastern Britain away. We certainly can't build underwater walls to prevent the ice from destroying from destroying the ocean currents, from destroying the ice. We also have to remember that this is a really hazardous area. There are huge icebergs here that will sink research vessels or any kind of infrastructure. These are absolutely massive icebergs that would destroy any kind of human infrastructure in their path. I don't think you can make seawalls to prevent ocean currents from getting underneath these glaciers. They're far too big, far too dangerous, and far too challenging. Iceberg A68 approach in South Georgia is really interesting. So iceberg A68 carved off one of the ice shelves on the Antarctic Peninsula a few years ago. And it's a really, really large iceberg, and it's approaching the subantarctic island of South Georgia. And South Georgia is really interesting because it's a biodiversity hotspot. It's also part of British Antarctic Territory. It's one of our overseas islands, but it's a hotspot for penguins, for seals, for whales, for albatross, a huge number of really special birds. There's the South Georgia duck, which is the only duck which is not vegetarian, which is quite interesting. And icebergs do periodically reach South Georgia because it's located just south of the polar front. So large icebergs do occasionally get here. And when they do, there is a detrimental impact on wildlife. And so we do see damage to the local biodiversity. We see reductions. Penguins tend to have a poor breeding season and abandon their nests and abandon their chicks. Albatrosses will probably be all right because they have very long they can fly really easily for a very long way, so they'll probably just change their fishing location. They're also quite clever to do that. And the whales will be fine, but there's likely to be a very detrimental impact on the penguin population for South Georgia if the iceberg reaches there and gets grounded near there and stays there for a long period of time, which is not guaranteed. So methane is probably more important from melting permafrost. So there's I've mostly focused on land ice, which is glaciers, ice caps, and ice sheets. But another big source of ice in the world is permafrost. And in parts of the Arctic that are not underneath glacier ice, we have large amounts of permafrost, which is where the ground is frozen for more than 2 years in a row. And that means that anything organic that lives there doesn't really decay, and it's just frozen in the ground. And this permafrost is melting really rapidly, and that's releasing large amounts of methane into the atmosphere. And this methane has a warming effect significantly greater than carbon dioxide. It is included in the models I showed you because we normalize methane and CO2 in those models. But the potential for extremely rapid releases of methane into the atmosphere from the melting permafrost is real and is a challenge. Methane seepage windows for glaciers. I don't think there's that much methane trapped underneath glaciers relative to permafrost. It tends to be the permafrost that we see as a more significant challenge. I am glad you found this useful for your A-level students. Please have a look at my website. My website is antarcticglaciers.org, and you'll find lots of teaching resources aimed at A-level students on the website. So if you're a teacher, there's plenty of information there. There is graphs and figures and teaching resources. There's maps and articles. They're all fully referenced with the latest scientific data. It's a project that I've been running since 2012, and it recently won an award from the Geologists Association for geological education. So please do have a look at Antarctic glaciers and send your A-level students there. I recently received some funding from the Antarctic Science Bursary to do some more educational resources, and so there'll be some Key Stage 3 materials on Antarctica and climate change coming out on Antarctic glaciers soon. We've got some really exciting collaborations with ice core scientists from the USA and from the British Antarctic Survey. We're bringing together some really great resources, some story maps, ArcGIS story maps aimed at Key Stage 3.